Okay, hello and welcome to my channel. Today we're going to be talking about quantum harmonic oscillator. This is a state where your potential is something like this. What is that? Okay, your potential is something like this. A parabola, or it is like a harmonic oscillator in classical mechanics. This is your V of x. And from that, you get your Hamiltonian, which is your energy would have a kinetic term and a potential term. M omega squared x squared. You would put it in operator form, of course. Oh my gosh. Yeah, here. There we go. That would be your Hamiltonian. Now we would put this in our time-independent Schrodinger equation. So in time-independent Schrodinger equation, wait, why did I wrong? Okay, there no psi, I'm sorry. Got confused for a little bit. So we put that. Okay, x squared plus omega squared x psi, that would equal to E psi. Right, so now you have this. And remember one thing that I told you in the finite potential square well is that unitary numbers will be your best friend throughout this journey. And here we're gonna see it again with our x now turn into a and u here is unitary. U is unitary, and a would have a unit of length, BL. So that is our x is, well, a value that has that determines the position. Therefore, this is completely viable for x. We just want the u though. And from here, one thing you can do is that you take the coefficient of both the potential and the kinetic energy, those two to be equal to each other, ma squared, because here you sub the x into a squared u squared. The a doesn't matter, so it get pushed out. It gets to there, and here is, well, m omega square a square. And from this, you can, well, get your a square to be equal to h bar over m omega. And this, the root of this, which is a, is root of h bar over m omega, and that is the characteristic length scale of your quantum harmonic oscillator, which is the length from, I think, center to the bound. Okay, so that is the characteristic length scale that you get from doing this. Okay, now we gonna hop back to our Schrodinger equation. So from here, 2ma squared d psi du squared plus m omega squared a squared u squared psi equal to e. Okay, now we sub our a in to get, well, get that. There you go. E of psi. Okay, I forgot the u square there. Alright, so you sub it back, you can cancel these two. Let me pull it over there, not really cancel, but you isolate these psi term, kinda. Psi. Now we take another energy variable that is an E like this, and you might have seen this in others physics class. So this guy to be equal to 2E, and this is unit free. How convenient. Right, and from here you get that your energy is, well, h bar omega over 2 of this curly E. From here, our Schrödinger equation would be rewritten as, we're gonna use this for a long time, so I will write it up there. D squared psi. Okay, that's okay. I forgot the square. Okay, so our Schrödinger equation will be rewritten as that. And from now, you still don't know how this, well, this system, when you send in a wave function, would behave when it reaches infinity, right? So that would be what we want to do right here. We would evaluate our u at plus minus infinity. And at plus minus infinity, it would have to, okay? So when u approaches plus minus infinity, it would have to be a decay. It would have to decay exponentially. And when you check the math, you do the double derivative, then you let u approach infinity. You can cross terms, and what you would be left with is something like this. What you would be left with is minus u squared over 2. Because if you don't know how it is, you would take the standard decay form, you derived it twice, and then you let u approach infinity. Then you can see which term is irrelevant and cross them, and in the end you kind of compare those two and get your coefficient. That would be the standard procedure for you to do this. Or if later on you might get like this intuition and you can just, well, know how it would look like. That is pretty hard. Okay, have to erase maybe this part. Right. So we got that part already. Our psi of u. Now we would want that to be in our wave function, right? For it to be plausible. But we don't know what is in here yet. We just know the term that we want. So to force this term to be present in our wave function, we would have to introduce another function of u called h of u. So this would force this term to be present. We would hope for this to be a polynomial, of course. And from that, we can start doing the math. So say that I'm going to evaluate this term first. That would be this term you can split. No, you have to split it. So we have to define two new functions, so you can do the u prime v plus minus v prime u thing. I'll do some calculus here. So u, take the classic f and g then. Yeah, that could work. So take f of u to this term and that term. Yeah, that is pretty good. Would be minus u of h, and we're gonna get the double derivative. Okay, u to where du square minus, minus h u dh du. Next is our g. G would take it to be the exponential term. G of u would be u squared over 2. And we derive this guy to give us this. Okay, that's not that clear, but that is the exponential. Okay, now we're gonna spread that u squared. Now we spread that into these smaller guy. I have to take that, the derivative. U, and this times our g. Oh my gosh, this is in the way. Oh no. Write it like that. Okay, and plus our f u of n times g prime. I'm just doing some calculus here. There we go. Got this. And you see that there is a common factor that is the exponential part. So you can factor that out. Alright. Now, why did I write the square bracket? Don't need that. That is d square u square h u u minus plus u square h. Yeah, that looks about right. And, now we can cancels out, group it again. Now h would be the common factor for these two. So that would be u squared minus 2u du. And the common factor here is h u squared minus 1. Okay, there we go. Now we sub it back to there. Oh no. Maybe I can just erase this as well. You sub it back. Cancel the, yeah, you can cancel that. No. There you go. You can now we're almost there. Now you would cancel the exponential part, then group this over here, and so you have that. You move that over there. What you get, the u square would be gone. So final form. Okay, I don't know if I wrote this correctly, but e minus 1. Pretty sure it is like this. Okay, so this would be that. Okay, this would be the form we would be working on. And that's it for today. This is part 1. I plan to split this into, well, 3 parts, since the harmonic oscillator is pretty important and it is super long.